Hi, this is a course on electromagnetism, and we're still on our lesson on capacitance, current, resistance, EMF, and Kirchhoff's rule. In this video, we are going to discuss about your current, resistance, and EMF. Let's start our discussion with defining your current. Current is any motion of charge from one region to another, and this is defined mathematically as your current I that's equal to dq over dt, the time derivative of the motion of your charges, and it has units of ampere. The electric field in conductor causes charges to flow, and this electric field is created by your potential difference or your source of your EMF. In the absence of an external field, your electrons move in random. Consider this electron here without internal or external electric field. This electron moves in random, just like in the blue line here. And if a field exists, its force on the electron imposes drift. So if you try to connect this one to a circuit, connecting this one to a source of voltage, then you create some field, and the field forces your electrons, imposing drift. So there is a motion, or there is a drift of your electrons into some displacement, but still the path of the electron with electric field still is mostly random. But again, there is a displacement due to your drift velocity. Your electric field does work on moving charges. It transfers kinetic energy to the conductor through collisions with ions, and it increases in vibrational energy of the ions, increasing in temperature. This is what you observe in your wires as your wires heat up. So if you try to connect your wire to some power supply, you'll observe that your wire actually feels hotter as time goes by. Much of the work done by the electric field again goes into heating the conductor, not into accelerating your charges. For your metals, you have moving charges which are negatively charged, or we call this one as your electrons. And for your ionized gas or plasma, or your ionic solution, you have positive or negative ions. And for your semiconductor, you have your electron plus your hole or your vacancy, which are your charge carriers. The conventional direction of your current flow follows your flow of your positive charges. Current produced by either positive or your negative charges. Moving charges in metals are your electrons. As you can see here, if you're going to connect your wire into a circuit or to a potential difference, and if this is a positive terminal and this is the negative terminal, the your positive charges move from your positive towards your negative because these charges will be repelled by this positive charge here, and they're attracted to the negative terminal. This is just opposing to the flow of your negative charges, where your negative charges are attracted with the positive terminal. Again, conventional current is treated as the flow of positive charges, regardless of whether the free charges in the conductor are positive, negative, or both. In a metallic conductor, the moving charges are electrons, but the current still points in the direction of positive charges flow. Suppose you have n number of charged particles per volume in a current element. Here, you have your current element for your conductor here. And then you also have your drift velocity vt, the drift velocity that you have talked about earlier, and your time element dt. And let's take some cross-sectional area A in your current element. Okay, so you have this cross-sectional area A here. Now your dq, this is equal to your q times your number of charged particles per volume times your area times your drift velocity times your time element dt. And since your I is equal to your dq over dt, then if we substitute the value of dq into the equation, then we have nq times the area times your drift velocity vd. This is your current I, which is a scalar quantity. We can also define your current density J, which is a vector quantity, since as you can see, your drift velocity is or can also be a vector quantity. Your current density J is equal to your I divided by your area A, and that's equal to your NQ times VD, which is a vector quantity. The unit of your current density J is in amps or in ampere per meter squared. Thicker wire can carry more charges at the same drift velocity. As you can see from the equation, which is your I that's equal to NQAVD, if you have a greater area A, then your current I will also be greater. You increase A, you increase the ability to carry current. And note that this is the same for your current density J. As we have said in the previous slide, thicker wire can carry more current, and you can rank your wire diameter by your gauge. As an example, you have number 3 gauge, which can carry around 100 amperes of current, number 6 gauge of around 65 amperes, and you have number 14 gauge, which can carry only around 15 amperes of current. And you have this measuring tool here to measure the diameter by gauge of your wire. So if you're going to buy wires in electrical supply store, you are sometimes or you are asked of the gauge of the wire that you are buying, and this is what your gauge actually means. So the smaller the gauge is, the smaller the number of the gauge is, the greater the current that the wire can carry. The resistivity of a material, on the other hand, is the ratio of the electric field in material to your current density it causes. That is, your resistivity rho is equal to your electric field over your current density J. The larger your rho is, you have a large field needed to generate a small current. And the units for your resistivity is in ohm meter, which is your ohm meter is equal to your volts per meter times your ampere per meter squared. So you have volts per ampere times your meter. Remember that 1 ohm, this is equal to your volts per ampere. And again, for your resistivity, if you have a large resistivity rho, then you need a large field or a large electric field in order to generate just a small current J. These are some of the resistivities of different materials at room temperature at 20 degrees. And as you can see, for conductors, they have the smallest resistivity. Okay, silver has the smallest one, and then for your alloys, which are um, combinations of your metals, okay, you have still a small resistivity of order 10 to the negative 8. And for your semiconductors, as you can see, the resistivity is in between that of your insulators, where your insulators have resistivity of around 10 to the 14 or 10 to the 16 range. Wood has a resistivity of around 10 to the 8 to 10 to the 11. Please observe that the resistivity of your semiconductors are very interesting. It's not quite small. It's also not quite large. This is the reason why your semiconductors are used widely in your electronics industry. But we are not going to dig into deeper into this one as of the moment, and we're going to discuss about this one in the next lessons. Metals are good electrical and thermal conductors. There is a very large difference in conductivity of metals versus your insulators, as you have seen earlier. Semiconductors, on the other hand, have intermediate resistivity between your metals and then your insulators. Your conductivity is just the inverse of your resistivity. The resistivity and your temperature has the following relationship. You have your raw for your the resistivity at a specific temperature that's equal to your initial resistivity rho naught times 1 plus alpha times T minus T naught. And here again, your temperature is any temperature, and then your T naught is your initial temperature. Here, alpha is the temperature coefficient of resistivity. And for metals, your resistivity increases with temperature. That's why it's not good for um, your your appliances if you are using it for a long time, and when your appliances already are heating up, then that means you are actually consuming more electricity because of the increasing resistivity with increasing temperature. Semiconductors have resistivity that decreases with the temperature, and for your superconductor, which is a special type of a conductor, has a resistivity that first decreases mostly with decreasing T and becomes zero at the critical temperature T. The highest critical temperature observed in the year 2009 is around 230 Kelvin, which is your EA or your TBCC. Oh, this is the graph for your resistivity with temperature for metals. For semiconductors, the resistivity decreases with temperature. For superconductors, at temperature below the critical temperature, the resistivity is just zero. So it first decreases smoothly, and then it drops at the specific critical temperature Tc. These are some of the temperature coefficients alpha of your resistivity. For example, you have your aluminum of 0.0039, and take note here of the negative coefficient of resistivity of your carbon or graphite, because your carbon or your graphite is a semiconductor. The resistance of a conductor, R, is equal to your resistivity times the length divided by the area. The units of your resistance is in ohms, and you have here your omega for the symbol of your ohms. And in your resistors, you will observe that your resistors have the following color codes. And this is what your color codes for resistors represents. So you have here, as you can see, for example, this has 4 color bands. So usually here, the color of this one is in gold, or you also have this one in silver. This is your tolerance. And the first one is the first digit. The second one is your second digit. And third one is your multiplier. So these are your values for your digit, and then these are the values for your multiplier. And then lastly, you have your tolerance. You will have a separate activity for this one in reading the resistance of your resistors using the color codes. For example, green, the first digit, has a value as a digit of 5, and the second digit, violet, has a value of 7. So you have 57 times the multiplier, which is red, which is around 10 to the 2. So you have 57 times 10 to the second power, that is around 5,700 ohms, or that's equal to 5.7 kiloohms. And since this is silver, this is a tolerance of around, or this is a tolerance of plus minus 10%. Gold has a tolerance of 5 Now, these are some of the equations that we have so far from our previous slides. You have your current I, that's equal to your current density J times the area. You have your voltage, which is just your electric field times your length. And if you have this two here, then your electric field is equal to the voltage over your length. And this is equal to your rho times J. So you have rho I over A. And as you can see here, for your voltage, you have rho dot L over A times I. And your rho dot L over A here is just your resistance. Okay. This is your resistance R. Then we have your V equals IR. And we have your Ohm's law for your conductors. The unit again for your resistance is in ohms. So you have here the most important equation that we can use here so far, which is your V equals IR, which is your Ohm's law. But your Ohm's law is actually not a law that applies every time, because there are cases that your Ohm's law is not valid. For an ohmic resistor, such as a typical metal wire at a given temperature, the current is proportional to the voltage. So you have this Ohm's law here, where your voltage is directly proportional to your current I. And if you take the slope of this one, you have your 1 over R, your 1 over resistance. This is where your Ohm's law holds true. But if you have a semiconductor diode, which is a non-ohmic resistor, your Ohm's law will not anymore be valid. And you have here the graph of your semiconductor diode. In the direction of the positive current and positive voltage, I increases nonlinearly with V. Initially, it increases exponentially, and there is a surge of increase of your current as you increase your voltage. In the direction of a negative current and voltage, there is little current flow. This area here is what you call your forward bias, and this area here is what you call your reverse bias. We are going to discuss more about this graph in the next lessons. These are some symbols for circuit diagrams that we will use in analyzing networks in the next lessons. You have here a straight line for a conductor with negligible resistance. This one here is used for your resistor. Two parallel lines where the other one is shorter, and you can have a plus sign on the longer line. This is the source of EMF, okay, where the longer vertical line always represents the positive terminal, usually the terminal with higher potential. This one is used for a source of EMF with internal resistance R. This one is for a voltmeter that measures the potential difference between its terminals. And this one is for the ammeter that measures the current through it. Real sources of electromotive force actually contain some internal resistance R. Like say, for example, for this battery R here, or for this battery here, this contains some internal resistance R. And that means that you can only measure the terminal voltage of your EMF source. And the terminal voltage, VAB, is equal to your epsilon minus your IR. And let's say, for example, your battery has a label of 9 volts. But if you now take your voltmeter and measure the potential difference across your battery, you only measured around 8.9 volts. And it's only 8.9 volts even if it's new, because a real source of EMF contains some internal resistance R here, which subtracts some potential to your battery. The terminal voltage of a 12-volt battery is less than 12 volts when actually connected to the light bulb. The rate of energy that is delivered to or extracted from a circuit element is your power P, and that is equal to your terminal voltage VAV times I. Your power has units of watts. Power delivered to a pure resistor is equal to your power P is equal to I squared R, or you can also use your terminal voltage VAB squared over R. So this is how you're going to calculate the power or the rate of energy that is delivered to your circuit element. So you have here again your power, which is your terminal voltage VAV times I, and that means that you have your voltage A minus your voltage V times I. It has unit in watts. 1 watt is equal to joules per 1 joule per second. And the potential input of your resistance is just your voltage, your terminal voltage times your I, or I squared R, or you can also use VAB squared over R. And the potential output of the source with internal resistance is just your epsilon minus IR times I for your terminal voltage, or that's equal to your epsilon dot I minus I squared R. Here, your epsilon I is the rate at which the source converts non-electrical to electrical energy. I squared R is the rate at which electrical energy is dissipated at the internal resistance of the source.